Thank you for welcoming me to this conference. I'm excited to be part of this important discussion and see where it goes in the future. So the science of landscape ecology is really challenging. In my opinion, it's one of the most critical knowledge systems that natural resource managers need in their work. It challenges us to strive to understand nature and how we can live and work within the capability of the landscapes that we encounter. Climate change is throwing a few monkey wrenches into our knowledge system, but I think that challenge too just keeps us, exacerbates the need for us to be incredibly inquisitive and constantly learn and evolve in our thinking. And if we're wise, approach land management with humility. So today I want to introduce you to some new and developing tools that highlight geomorphic and soil information on National Forest System lands in Region 6, the PNW. I'll present new mapping that has been done to delineate land type associations. These delineations help resource managers organize landscapes into smaller units that are similar in function. They characterize the inherent capabilities and limitations of different landscapes and help managers make wise land use decisions that are based on this ecological knowledge. I'll provide a few examples from the regional to the landscape to the site-specific level for use in project development. So the U.S. Forest Service has developed a terrestrial ecological unit hierarchy. It's a classification of mapping that stratifies the Earth into smaller and smaller areas of increasingly uniform ecological potential. The terrestrial unit hierarchy nests ecological units, just as the hydrologic unit classification nests smaller watersheds within larger watersheds. You can see by this slide, however, that, I need help.
Is the clicker?
Where's my, I always get the TV clicker upside down as well. Anyway, you can see that there's a huge blank at the landscape level. We have other ecological units, but we have a blank at the landscape level. And I believe that this national hierarchy is really important at all scales, but in my opinion, the landscape scale is the scale that we need for forest management, and it provides the context for management and restoration of our landscapes. So to fill this gap, we developed land type association mapping. This project brought ecoregional mapping that's already been compiled and published into a more refined level. Upcoming forest plans and also the terrestrial ecological unit assessment both use land type associations as their analytical scale. The LTAs help us classify map units into areas of similar function. They help us organize landscapes and understand the arrangement and the patterns and the capabilities of various portions of the landscape across ownership boundaries. They're the scale at which soil forming factors take place. Ecologists call those state factors. If you've had a basic soil class, you all know the soil forming factors. This scale of mapping helps resource management understand the inherent capability of landscapes, the process drivers, the sensitivities and the resilience of landscapes to both natural and human impacts. So there's two components that were put together to develop the LTAs. The first is potential natural vegetation mapping, and we used Jan Henderson's work and Mike Simpson's work of potential natural vegetation modeling based on the local district or forest ecologists' reference to which of those models they thought best represented their landscape. I know that the ecologists are currently remapping potential natural vegetation, so the land type association boundaries may change in the future, and that can be incorporated. The second component of LTA mapping is what we call land form associations. These are the geophysical components of the land type associations. So you need to know both those words, land form association and land type association. So I'm most familiar with the land form association, and it's what I'll focus this presentation on. For me, this land form association mapping is an entirely new look at the region. And what's new and unique, I think, is that it focuses on geomorphic processes that occurred and help shape and form the landscapes. So I've been working in natural resource for the last 40 years, and I've learned a ton. But when I was helping Dr. Jay Noller from OSU with this work, I learned more about the Pacific Northwest than I'd ever known before. And I also learned about the hierarchy, the value in looking at ecological units in a hierarchy and using ecological units to set the context for landscape restoration and management. So dissecting the landform association map, I'd like to just show you some of the background components of it. And one of the key components of it was a grouping of geologic groups. The base geology of the PNW is quite complex. So you have the Columbia River Gorge volcanics, the third largest flood basalt flow in the world, covering most of eastern Oregon, southeast Washington, and the Columbia Gorge. Then you have the metamorphic terrains that have floated in on the subduction zone. So they're really making unique landscapes. Then you have the ocean sediments that have been uplifted in the sedimentary units. You have glacial deposits, flood deposits that create really unique landscapes. And you have marine uplifts of sediments along the coast. And once you look at this geology, you start to understand things like the weathering capacity, the topographic controls, geochemistry that really alters some soil characteristics and water characteristics. You start to think about landscape stability and even how groundwater is moving in your system. My friend Mark Kimsey at University of Idaho, he coined the term good rocks, bad rocks. And I think it's important to think about that when you're thinking the effect of geology on your systems. And to very, very simplify his concept, it's basically that rocks that are more highly weatherable and have dark-colored minerals provide sufficient nutrients, and he termed them good rocks. And other light-colored rocks, rocks that are really slow weathering, are termed bad rocks. So surface geology could be entirely different than the base rocks, especially in the Pacific Northwest, where volcanic ash and pumice have covered the landscape. This map shows some of our most well-known deposits, Mazama and Mount St. Helens, but those are only two volcanic tephra flows of the 16 major volcanic peaks in the area. Recently, NRCS has been mapping Mount Rainier National Park, and in one soil profile, they found 40 different tephra deposits on the north side of the mountain. So areas where these pyroclastic volcanic ash eruptions have blanketed the landscape have really influenced the qualities of that landscape. For instance, much of the Blue Mountains is covered with ash, and it's very important for the type of vegetation that's there, especially when it comes to water holding capacity. So volcanic ash has many unique properties: water holding, thermal properties, the nutrient retention properties are all really unique with ash. And we here in the Pacific Northwest, Alaska, and Hawaii are really the portions of the United States where volcanic ash dominates. So surface geology, too, can be entirely different than the base rocks if you're thinking about the geomorphic processes that have shaped those landscapes. Much of the region is glacial deposits, that's shown in the blue on this area. So Dr. Knoller delineated all of these landscapes, and is influenced by glaciation and also influenced by mass wasting, these gray areas. And mass wasting doesn't always, in our LTA mapping, means both landslide deposits and waterborne erosion. Then you also have the marine sediments along the coast, creating the dune systems and the marine terraces and benches. These brown areas, you have very strong tectonic uplift where bedrock controls weathering, and topography has a topographic control on the landscape because of the competent bedrock, and those are scattered throughout the region. Fluvial processes have created some of the larger valleys, and then lacustrine processes have dominated in the basin range area, and also volcanic processes dominate in some of the high cascade systems and then much of southeast Oregon. These geomorphic processes left unique and individual signatures on the landscape that are characterized by rock outcrop, rock exposure, landscape stability, soil depth, soil texture, rock fragment content, and ultimately they influence soil fertility. So here's an example of the landform association mapping. And I think that many ecological and watershed processes can be explained at the land type association level. For instance, here in the dissected high mountains, you have competent bedrock, shallow soil, and well-developed stream systems. Thus, the areas can be expected to shed water or snowmelt quickly, and they have low storage capacity. Rock outcrop is usually a component of these areas, and forest productivity is somewhat impacted by the shallow soil system. On the opposite end of the spectrum, you have these hummocky mountains, which are earth flow terrain. We sometimes call them variegated mountains in the land type mapping. They have more developed, deeper soils with clays that store water. These areas lack well-developed stream systems because of the contorted hydrology, since these systems are slowly moving over time. They can be chronic sediment producers if a stream is undercutting the toe of these areas. They can also be cold water sources and low-season flow sources of water. Another example of landform associations is these angulate mountains. Angulate mountains are bedrock controlled. They have steep scarp faces on one side and sediment on the more gentle back slope, which often have shallow landslides that trend with the angle of the rock. Channels tend to migrate towards the scarp face of these, so any roads constructed on the scarp face are prone to debris torrents as the slopes get undercut. Channels tend to have a stair-step morphology because of the bedrock control on these systems. I find this area of Mountain Valley really interesting. This is a valley that was uplifted during the Coastal Range uplift. And you can see in these really smooth areas here, the valley is filling itself with sediment as it's head cutting into this mountain system. Into the headwalls here. And this is a great source of sediment for the Illinois River and the Rogue-Siskiyou National Forest. Lastly, in this picture, we have smooth-crusted rivers. This is a rock type that is more highly weatherable. Soils are deeper on this area. You'd have high productivity. And you can see there's not very many incise streams. Groundwater goes into these systems and is expressed as soil water or groundwater. So Kim Mellon used the Landform Association to look at several species of wildlife habitat and to see if they could be a predictor of where they might find that habitat. So in this example of the white-headed woodpecker, she found significant, statistically significant correlations with land type associations in the Blue Mountain area. But then if you think about the white-headed woodpecker, they only visit ponderosa pine sites. So then when you bring in the vegetation component, the land type associations, you can further refine where those species, where there's potential habitats for those species. And so if you're doing survey and monitoring, you can focus your activities and save money and time for the Forest Service. So this is a project that Terry Craig did on the Sisters Ranger District. And it was a project that had the focus of improving forest health and reducing fuels and also improving deer winter range. So the fuels people, of course, wanted to thin the forest and burn and mow everywhere and reduce ladder fuels. And, you know, it's right outside the town of Sisters, so it was a really high-profile project. And so they just wanted to thin out everything and make it a really clear forest floor. But then the wildlife biologist came in and says, well, you know, there's deer here, and we need winter range, and we need forage for those species. So really their prescriptions that they would have come up with were in conflict with each other. So Terry, using the LTA and the Deschutes soil resource inventory, kind of brought some of his ecological knowledge to the table and helped them both meet their objectives. So here in this area in the west is a lava flow coming off of Middle Sister, maybe, one of the three sisters. So there's lava ridges in here. It's higher elevation because it's closer to the crest. It supports manzanita and ceanothus. And so in this area, it wasn't as important for deer winter forage, so they chose to mow a lot of the ceanothus and manzanita, and then because of the lava ridges, there were areas where it was really thin soils over rock, and then these deep pockets where ash had accumulated. So they kept the old growth and some of the hiding structure in the deeper soil pockets that could support that kind of vegetation, and then created gaps across the landscape surrounding the lava ridges, which were less able to support dense vegetation. The second soil group that they looked at, the next group was area of glacial outwash with a consistent layer of Mazama ash over it. So water holding capacity and nutrient capacity throughout that area were very similar. So it left a lot of options for the planning group. It did support bitter brush, so they chose to mow kind of in succession, thin out the trees, and create gaps in certain places, but maintain the bitter brush that was high quality, and then improve the degraded bitter brush habitat. And then the final area had less rainfall. It supported bitter brush as well, but it also had juniper on it and sage, which were more resistant to fire because of a thinner ash content and more rocky soils. So they were able to thin, widely spaced in that area to honor the capacity of that land to support vegetation, because it didn't have a very high water holding capacity. So in the end, it was a project that people supported, and everybody seemed to get the management objectives that they were looking at. So a couple more examples. This is an example not so much of using the LTAs, but of using soil survey information, which is a finer level of ecological unit mapping. So low soil moisture in combination with high elevation evapotranspiration demand induces significant stress on forests. It increases the vulnerability of attacks to insects and disease and to wildfire. natural resource managers need to understand water storage and supply across forested landscapes. So climate and evapotranspiration themselves, I feel, is not enough. So we were able to use existing data sets to aid the planning efforts. And we took the soil resource inventory information and looked at available water supply, soil depth, and then used climatic information to look at evapotranspiration. And then with that information, we created a droughty soil index for the Pacific Northwest region. And so this enables you to really focus your treatments in on these areas that are potentially droughty. This is a landscape level document, so when you're really out project planning, you would have to refine some of this, but it gives you an idea of really where to focus in. These areas on the Wallowa-Whitman have ash in them, so they do have a higher water supply capacity. But it's another tool that we can use. So the other thing is there's signatures in the soil of historic landscape condition. And this is an example of mollisols being formed on the Wallowa-Whitman National Forest. Mollisols are deep, dark, organic rich surface horizons in the soil. Forests do not create this kind of soil. Grasses create this kind of soil. So we know that this soil developed in a grassland. And now when in this planning area, the planning team went out with a bunch of local ranchers, and the ranchers are like, this used to be a beautiful grassland, now it's just crowded with trees. And if you want to take the cows out of the riparian areas, you really need to restore these grasslands. And so we have these signatures. We can use these signatures and knowledge of our ecosystems, but we don't. Because the wildlife biologist comes in and says, no, we need 40% canopy cover, because we need 40% canopy cover everywhere, evidently. So I think we should start to use our ecological information. Maybe I hit a something there. So anyway, in summary, the 2012, there's lots of institutional policies that are leading us in the direction of really using ecological information. The 2012 planning rule requires us to use that information, and we all have the responsibility to understand the information we have. LTAs are new. We're going to have to learn what they mean, how we can use them, and then refine them as they're needed. Each piece of land has its own signature, and we need to take this opportunity to use land type association mapping, soil surveys, other ecological maps, and bring our core knowledge forward into the discussion of new planning efforts. Only by doing so can we be assured that we incorporate this ecological information and link natural resource management with ecological science. And by doing so, we'll lead the conversation and shape our landscapes of the future. Thank you.
Time for one question. John.
Where can we access this data?
The question is, where can we access this data? This data is on EcoShare, and it is, are you Forest Service?
No.
Okay, it's on EcoShare. And we're also trying to get it published, so it'll be peer-reviewed and be readily accessible for people to use.
Okay. Thank you.
Okay, thank you very much.